Here is Lesson 4 of Unit 6, Weathering and Soils. So we've talked about weathering and erosion before. I just want to review a little bit. I want to make sure that everybody knows that weathering and erosion are not synonyms. These two words don't mean the same thing. Weathering refers to the breakdown of rocks into little chunks of the same rock called sediment, and then erosion is the movement of those sediments somewhere else from wherever the weathering took place. So you can see in the diagram, weathering causes the rocks to break down. Erosion will cause the sediments that broke to move somewhere else from the parent rock where the little sediments broke away from. Weathering and erosion can be carried out by processes associated with wind, water, ice, gravity, and even some types of organisms. We're going to be focusing more on weathering than in erosion in this lesson, so there are two main types of weathering. The first is called mechanical weathering. Mechanical weathering occurs when some type of physical force breaks down rock into little chunks of sediment. So you can see here, big rock broken into smaller pieces, broken into even smaller pieces. That's an example of mechanical weathering. Another example from your own life would be like taking a piece of paper and ripping it in half. It's still paper, it's just broken into two smaller pieces now. Mechanical weathering is typically going to occur faster in cold climates, which we'll learn about in just a second here. Our first type of mechanical weathering is called frost wedging, and this is the reason why mechanical weathering happens more rapidly in cold climates, because frost wedging is the major player in the mechanical weathering game. So frost wedging occurs when you have a little crack in a rock, liquid water gets into that rock during the day. During the night, it gets colder, that water freezes, it forces that crack open a little bit wider because we know that ice expands when it freezes. And then as that crack is forced wider over time, water can get deeper into the crack, force it open even wider, and eventually it can crack entire boulders in half like this. And I put this little piece here, this is how potholes form, because we have this problem in Montana. We get potholes that form, little crack in the road, water seeps into the crack, forces that crack open wider, water seeps in again, forces it even wider, and then cars driving over the top of those cracks can break chunks off. So potholes form from frost wedging. Another type of mechanical weathering is called abrasion. This occurs when you have rocks that are scratching against each other. Soft rocks are more susceptible to this, so something soft like marble is going to be weathered by abrasion more than something harder like quartzite or granite. This is especially common in riverbeds because you have the water pushing all the rocks along and they're kind of grinding against each other, they're abrading each other, and this produces characteristically very rounded and smooth rocks. So whenever you think of river rocks, like if you went to a river and picked a rock out of the bottom, you get this nice smooth rounded rock. That's due to abrasion. Next type of mechanical weathering is unloading. This is much less common than frost wedging. Unloading happens when you have some rock mass that formed underground, maybe like a batholith, an igneous batholith, and then over time the material above that large rock mass is eroded away over top, and so the pressure is reduced on that rock. And that causes this phenomenon called exfoliation, where the rock will kind of peel away in layers like an onion. Another way that mechanical weathering can occur is through biological activity of plants or animals that break up rocks. So when plant roots grow into a rock, like you can see in this picture here, that's a process called root wedging because the roots work their way into little cracks and then the roots grow, push the cracks wider, and break the rocks up. Animal burrows can also cause some weathering and erosion of rocks. So for example, this is a bird called a cliff swallow, and these birds dig little holes into cliff sides of soft rocks, especially things like sandstone, and make their little nest in there. The other main type of weathering is called chemical weathering, and this involves breakdown of rocks into different substances that actually changes the composition of the rock. So for example, think of burning a piece of paper. It's not paper anymore, it's a little bit of like soot and ash and stuff. So ripping the paper was mechanical weathering, burning a paper is chemical weathering. Chemical weathering involves water oftentimes, and then chemical reactions are sped up by warm temperatures. So chemical weathering occurs fastest in warm and humid climates. Our first type of chemical weathering is acid rain, and acid rain forms when water in clouds mixes with pollutants. So we have in this diagram here, we have pollutants coming from the tailpipe of a car, coming from a factory, things like carbon dioxide, sulfur dioxide, and nitrogen oxides will go up into the atmosphere, mix with the clouds, turn the water in the clouds into a slightly acidic solution, and then when that water falls as rain or snow or something, it's acidic and can dissolve stuff. So acid rain is really good at dissolving things that are calcium rich, like limestone and marble. Here's an example of some limestone out in nature. You can see this pitting effect of where little pools of the acidic rainwater collected and then dissolved the rock. Marble is used as a decorative stone a lot because it's very beautiful, but it's also very susceptible to this acid rain weathering. So this is a statue that's face was kind of melted off over time by acid rain. And then this is an example showing you the difference between rock types and their susceptibility to acid rain. This is a tombstone from 1868 made of granite. You can see it's hardly weathered at all. You can still read everything on it. This is a tombstone that's younger. It's from 1872, I believe, but a lot of the writing has been dissolved off of it by acid rain. Because it's made of marble, it's more susceptible to the acid in acid rain. So kind of similar to acid rain is acidic groundwater. This is not usually caused by pollution. It can be if you've got like acid mine drainage or something like that, but acidic groundwater can form when you've got minerals in the ground, in the soil that mix with the groundwater and lower its pH, and then that acidic groundwater eats away at rock below the surface, and you get what's called karst topography, which is areas characterized by lots of caverns and sinkholes. Here's a diagram showing some sinkholes, some caverns underneath the ground. This map shows where areas of karst topography are present. So we have some in Montana. Down here in Florida, they've got it really, really badly. Here is a picture of Lewis and Clark Caverns. So caverns form when you've got acidic groundwater that dissolves away the limestone. Lewis and Clark Caverns is all limestone formations. And then here's an example of why it's not great to live over karst topography is because you can have a sinkhole that forms under your house and then it'll just decide to collapse and your whole house falls in. Next type of chemical weathering is called oxidation, and this is when you have materials, specifically types of metals that are present in rock that will react with oxygen in the air and change color. This is also called rust. So when you have a rock like this that turns orangey, like an orangey red color, you can tell that there's a high content of iron within that rock. When you have rocks like this that turn a greenish color over time of being exposed to air, you can tell that they have copper contained within the rock. Last type of chemical weathering is through biological activity. There's a certain type of organism called a lichen, which is essentially a symbiotic colony of algae and bacteria and fungi that all work together. And these things chemically digest rocks and eat them to get their minerals. So these are just some examples of what lichens can look like. These are pretty fancy lichens. This is probably the most type of lichen that you'll see in Montana. So now moving on to soils. Soils are probably the most important product of weathering on Earth because soils support human life. If we didn't have soil, we wouldn't be able to grow crops, we wouldn't be able to graze animals to eat, we would starve to death. So soil is part of what's called the regolith, and the regolith is just a layer of chunks of broken down rock and stuff that's covering the whole surface of the Earth, and it's the part of the regolith that can support plant growth. So the composition of soil. Soil is made of four main ingredients: minerals making up 45%, organic matter or humus, this is stuff like dead leaves, dead bugs, makes up about 5% of soil, and then water and air make up 25% each of soil. And the composition of soil is really important for plant growth because it needs to have a good balance of minerals that are important to the plants, organic matter to be broken down, and then water and air to support the root system of the plants in order to get solid plant growth. So the texture of the soil is also important for plant growth because soil texture is largely going to determine the drainage of the soil, and drainage is important because you don't want water pooling up too much in your soil. You want it to be able to drain out so that the plant roots don't get moldy and drown. But soil texture is based on the particle size and the amount of those particles that are contained within the soil. So basically we break it down into four groups of particles called clay, loam, sand, and silt. And those make up a bunch of different types of soil. And so you can use this handy dandy little soil pyramid thing here that bases percent silt, percent sand, and percent clay to find out what kind of soil you've got going on there. So say we had a soil that's 20% clay, 40% silt, and 40% sand. The way you use this pyramid is find which side you want. So 20% clay, we find the 20% here, which means we're along this line here somewhere, okay? So then we've got 40% silt, here's the silt side, so now we're along this line here. So we care about where these lines are crossing. So this 20% line and this 40% line are crossing in this loam region here. And then we also have a 40% sand content in our soil. So this point right here, smack dab in the middle of the loam soil type, is 20% clay, 40% silt, and 40% sand soil. So something that we can use to look at kind of the health and development cycle of soil is called a soil profile. Since soil is going to vary in its composition, texture, structure, and color at varying depths, the more mature a soil is, the longer it's been forming, the older that soil sample is, the more distinct this soil profile is going to be. Soil profiles are broken into horizons based on kind of the chemical makeup of the soil, what's going on there. So at the top, we have the O horizon, which O stands for organic. That's just like undecayed organic stuff, so leaves, things like that. Beneath that is the A horizon, where we've got basically the topsoil. This is the really good soil that the plants get a lot of nutrients out of. Next, we have the B horizon, which is an area that's a little bit more depleted of minerals, but plant roots, as you can see in this diagram, can reach all the way down through the B horizon. Next, we have the C horizon, which is partially broken down parent rock material, and then beneath the C horizon, we have the R horizon, which is completely unweathered hard bedrock. So naturally, we couldn't talk about soil without discussing soil erosion. Soil erosion is when soil is moved, mainly by water, from wherever it was to somewhere else. So this process happens naturally when like raindrops hit the ground or little surface water processes pick up soil and carry it somewhere else. But nature has ways of keeping this from happening, mainly using plant roots. But humans, since we ruin everything we touch, we go and dig up all of the plants, like all of the native plants. And what do? We plant crappy little Kentucky bluegrass as our lawn. Look at how shallow the root system is here. You can't even hardly see it on the diagram. Compared to all of these native prairie grass root systems, the thicker the root system, the deeper they reach, the more firmly they hold the soil in place to help it resist erosion. Here's a guy holding up a chunk of native prairie grass next to some wheat crop. You can see how absolutely ridiculously tiny the root system of this wheat crop is compared to the native prairie grasses. So native prairie grasses are so incredibly good at sequestering carbon out of the atmosphere. They suck the CO2 out of the atmosphere and store it in their roots. So planting native prairie grasses and letting some of the land return to its wild state with these deeply rooted plants can help to mitigate some of the problems that we're creating by putting too much carbon dioxide into the atmosphere.